Okay, today we are kind of as you are kind of finishing up your mover um, code, we're moving on to the penultimate topic, which is random variate generation. And there are two layers to random variate generation. The first is what I'm called random number generation, or strictly speaking, pseudo random number generation. And then the second is random variate generation. And after today, you'll know what that difference is. You've all no doubt worked with a computer generated pseudo random number generator before, at least those of you who suffered them. Oops. Those of you who why aren't you showing? I guess it helps if you plug it in. No. All right, let's try this again. Okay. Hello. There we go. Okay, two layers. And you've all, well, if you remember last quarter, those of you who were in the Java class, we're dealing with that. And we're going to kind of, and then I promised we'd kind of peel back the hood a little bit, and that's what we're doing right now. So, well, the first thing to understand, and this is why the term pseudo is put as a modifier, is that it is literally impossible for a computer algorithm to create a genuine random number sequence. It is impossible. Can't happen. And it's provable to not happen. And so why don't we just sort of quit and go say, well, can't do it, so that's it. Well, because of, I guess what I like to call the duck principle, which is, if it kind of walks and talks and quacks like a random number sequence, then we can treat it as such. So in other words, a pseudo random number generator is one that generates values that, strictly speaking, are not random, but look random. And what does it mean to look random? Basically, there are a battery of tests that you can apply to a sequence to say, what does it mean to be random? And this is those of you who've, if you recall from your statistics class, what is a random sample is what it was called there. You all remember what a random sample is, right? Okay, so independent, identically distributed random variables. So a random number sequence is a specific form of that. That is a sequence of a true random number sequence is a sequence of uniform 0-1 random variables. That's specifically what's meant by random number. A pseudo random number sequence is one that in many respects is statistically indistinguishable from a true random sequence. Now, there are random number sequences which are better than others. We're not going to delve into that too much, except to point out some that are good, some that are not so good and should be avoided in certain situations. And what random variate generation is, as we'll use, is taking these uniform 0, 1 random numbers and turning them into a distribution that we want. So all quarter long, we, and by we I mean you, have been using exponentials and uniforms and gammas, and which of course only scratches the surface of what possible distributions there are. And in the SimKit and in the Python versions, you simply said, okay, give me an exponential, and then you've pressed the I believe button that says, okay, this does give me exponential random variables. So this does give me gamma random variables. And they do, but I mean, subject to the caveat about the random number sequence not being truly random. But, like, I guess sort of the Animal Farm principle, all random number generators are equal, but some are more equal than others. Why aren't you? There we go. Okay. So a pseudo or a sequence, and U is the standard way of the standard letter that we're going to use. It's a random sequence if they are statistically independent, and each of them has a uniform distribution. So that's the theory. And then in practice, we want to create we want to use an algorithm, a finite algorithm that produces sequences that kind of look like this. And just to emphasize this a lot, computer algorithms cannot produce a truly random sequence. They simply can't. The kinds of things that can, there are quote truly random sequences. They are typically generated by some kind of physical process, such as decays of radioactive atoms and things like that. In other words, on the computer, can't do it, but we can do it approximately, and produce ones that are, as I said, statistically indistinguishable from a random sequence. And that can still be a little tricky. There have been random number generators that have passed a certain number of statistical tests that turn out to actually be not so great. Okay. So every pseudo random number generator works pretty much the same way. You have it actually generates, even though the output is typically uniform 0, 1 random numbers, what it actually produces is a sequence of integers. And these integers start from an initial value, and that's what we call the seed. So the seed is the starting place of this sequence of integers. And the problem with a finite algorithm producing these values is that eventually they repeat. Because it's a finite algorithm, eventually it'll create the same output. And once it does, it'll basically repeat the same sequence again. The term for that is the period. So the period of a random number sequence is how many separate values it can produce before it starts repeating itself. Now, understanding that, you see that if you use the same seed to start the sequence, then you'll generate the same values. I think we actually showed this a little bit last time, but we can, you've seen this in the computer programs that you've written, where when going all the way back to the arrival process, where you said, okay, we have an arrival process, inter-arrival times will be exponential. And as you're running it, every time you ran it, you got the same arrivals at the same times, right? Unless he did something a little extra. So it's these integers that it produces, and of course we want to maximize the period. We want to make them long values. We want to use as big a word as possible. And then what we what we do to produce the uniform zero ones is we divide it by a certain quantity. Now, the oldest version of this is something called a linear congruential generator. And this was, I mean, up until fairly recently, these were kind of what were mostly used. So, and it's what's nice about it is it's just really easy to understand. And then for certain values, it kind of produces streams that kind of look fairly decent. So we start with a certain seed. Let's call it I naught. And then the next value is produced by taking a linear transform of this. So you multiply it by a certain quantity and add another quantity, and then modulo the whole thing by some value m. And when you do, if you remember how modulo arithmetic works, what that means is that the values, the potential values, will always be less than m, strictly less than m. And so if we divide those by m, these values will always be between 0 and 1. Now, the period is going to be this value m. And that's usually a little too small for modern applications. So now, one of the most shocking things for me in recent times, because there was a project where I was kind of more or less forced onto it, where there was a Visual Basic application that they wanted converted into Java. And that Visual Basic application used the Visual Basic random number generator. And I was a little shocked to learn that the period was 2 to the 24th minus 1. Actually, that's fairly typical to have periods of 2 to a power minus 1 for various reasons. But that's shockingly short, ridiculously short. And as a random number generator, it also kind of, what's the technical term? Oh, it sucked. And that's not me saying there have been papers written that have analyzed it statistically and shown that it is not good. So, if you know, and now Visual Basic is actually, has a lot of benefits to it. So the lesson is, if you're ever using, if you're ever in Visual Basic, don't use the random number generator, whatever you do. Now, I'd like to say Java has a better one, but I can't really say that. Well, Java's is better than Visual Basic, but that is such a low bar that it doesn't, and as you know, I'm a Java file when it comes to that. But the random number generator just is not that great. It has a period of 2 to the 48th minus 1. That's in terms of period, that's a little bit better. But why? Kind of why drive a, I guess they don't make Yugos anymore. Why drive a Mini when you can drive a Lamborghini? So the pretty much the best random number generator out there today is something called a Mersenne Twister. It's been out for a while. And its period is this. And it's very, very random. It's passed all of the battery of tests for randomness that it has. And so rather than use the Java one, as I did earlier, when I learned about this, the one in SimKit uses this Mersenne Twister. And actually, just SimKit is kind of unique, the Java version, in that it actually has a number of different ones. It has the linear congruential one that was used by one of my first simulation programs was called SimScript, and so I reproduced that. Why? Because I had a bunch of models, and then by reproducing the exact random algorithm, I could then run models in SimKit and show that they had exactly the same output as what the SimScript ones were doing. So that was one thing. And this is one for Python. The Python default random number generator is a Mersenne twister. So that's why the Python version just uses the default one in Python. So it would be great if Java switched to that, but they didn't. So we're kind of okay. Now I want to address some myths about setting the seed, because one popular thing is to set this use the system clock to set the seed. So what does that give you? What that gives you is the ability is that every time you run your simulation, you're going to get a different result. You're going to get different numbers. Why? Because the clock keeps kind of moving along, and every language has a way of kind of getting that. Usually in Java, it'll give you a long, depending on the platform you're on. So for example, Unix or Unix-like systems will do their time in the number of milliseconds since January 1st, 1970, because that's when it came out. Whereas on Microsoft ones, it's sometime later, like in the 80s, the milliseconds since then. So and so the myth is, if you do that, that will make it more random. That will give you better answers. And it doesn't. It simply doesn't. And if you understand that, so here's how to understand it. So this would be the sequence of values, the total sequence of values generated by your random number sequence. And it's just this long series of integers that repeats eventually. And so if you fix a seed, so let's say we say, okay, we're going to fix the seed here, and what's the way that SimKit has been configured is that by default there's a default seed that it uses. It'll start at that place each and every time, and it will actually. And one of the reasons for using the random variate factory is that there's actually one single random number instance of the Mersenne twister by default. You can actually set it to other ones, but there's no reason to. So there's one that uses all of them. So when you instantiate your random variate from the factory, it makes sure that the random number stream that generates that is actually the same for all. And what that guarantees a certain independence. You see, if you think of a multiple server queue, you have arrival, you have a random variate for arrivals and random variates for service. If you didn't kind of do anything with a fixed, if you had separate instances of the same random number object, all starting from the same seed, then that would introduce correlation between the arrivals and the service times. And that totally screws up the values. By you only having one for everyone, then you're guaranteeing that they're at least going to be independent. And that's the default. Now, what if you don't like that? What if you're thinking, okay, bus is full of it, I need to kind of do something else. Well, what you can do with a little bit of effort, you can give each one their own random number stream and set the seeds independently of that. What's the danger of that? And for a random number sequence, as long as the Mersenne twistor, it's not as much of a problem. But in a serious simulation exercise or experiment, let's say, you're going to use literally billions of these generated values. And what you want to make sure is that they don't overlap. So let's say I say, okay, I know better than this. I'm gonna set my own seed. So let's say that my simulation uses these random variables, but then I'm going to set my seed, and for another, so for my arrivals, I'll use these. My service times, I'll use these. But now we have an overlap, and so we have unintended correlation here. And it's kind of a weird correlation between the arrivals at one time and the service times much later. What does that do to your statistics? I have no idea. But you want to make sure that you have complete independence. So by setting this, circling back to the system clock, what you've essentially, for a good random number sequence, is any segment of the generated values any better than any of the others? I mean, if it's a good sequence, it isn't. So if I choose the system, if I randomize by the system clock, and I think I'm getting more randomness than I'm getting, again, think of an simulation experiment where I'm using billions of these generated values, and I'm adding one more little bit of randomness to billions. Drop in the bucket, doesn't do anything. It's not that it's bad. It's that it just doesn't do what you think you're getting more randomness than you are. And you may be thinking, well, I wasn't even thinking of that until you mentioned it. So now that you know what not to think of, so don't. Now, there are situations where this is valuable. Now, I remember many years since I've, but I remember like we got our kids a Nintendo 64. I'm aging myself here, and then you played the Mario thing, and the thing about the anybody ever play the classic games, whatever, but if you remember in that, every screen was pretty much the same. Like when you kind of go into this one place, and then a bad guy would kind of come in and do this, and then the next time you go, okay, I know a bad guy is going to come in like this, and so I'm going to hop over it, and right, so you could play that game. Now, what if you're doing like a simulation-based training? Let's say that we're kind of trying to search rooms, and there might be a bad guy in there. So you go into the room, and then there's a bad guy over here, and you didn't know it, and you go in, and boom, you're dead. Okay, so now if you apply what I've been advocating here, which is kind of use the same seed, then the next time you go in, I know that guy's there, so I'll take care of it. And that's going to introduce negative training, right? So the next time you go in the room, he might be there, but he might be somewhere else. So the training in that case is kind of, and even if you're playing a game, I mean, when you're playing a game and you know how things are going to go, then it's not as much fun, or at least okay. So in those situations, then you want some kind of randomness, and using something like the clock is about as reasonable as you can do if you want things to be different every time you do it. But in discrete event simulation models, using for analysis, there really is no need for a random seed because it doesn't add anything. Okay, so see, I'm going to end a little early here, but let's give you more time to kind of finish your code. So, all right. So the recommendations about this are First of all, avoid Visual Basic in VBA, and also even Java's random number generator for production stuff. Now, if we're doing a classroom exercise or something like that, sure, that doesn't matter. If it matters, don't. Why? Because you want to make sure that you're using the best that's out there, and the best, as far as I can tell, that's out there is this Mersenne Twister. All major languages have a version. It was actually originally written in C. Somebody ported it to Java. That's the one I use. Again, Python, it's built in. So if you're using Python, you're good. If you're using a platform like C or C++, Visual Basic, one that doesn't have a good one, then basically Google Mersenne Twister and download the version for your platform. There is a Visual Basic version. The original one was written in C. So regardless of what language you use, there's no excuse to not use a kick-ass random number generator. And since both the Java and the Python ones that we're using here are using Mersenne Twister, so we can check that box in a sense. But if you're on another platform, what you want to do is find out what is the algorithm that's being used, and has it passed tests of its validity in terms of being independent and identically distributed. And you can't go by the brand. You think, well, Microsoft, I mean, that's a good brand. Java, that's a good brand, and so they must have a good one. Well, no. And in fact, just back in the day, there was a company called IBM. I think they're still around, but they were the Microsoft of the day, at least in terms of hardware. And back in the day, the dominant programming language was something called Fortran. And ask your grandparents about that. That was my very first language, and it was a really cool language. It, like all language, ever since the dawning of all this stuff, every computer language has had a random number generator in it, and the one in the IBM Fortran compiler, it was called Randu. It was a linear congruential generator. The same one, oops, where is it? Basically of this form. And, I said, well, it's IBM. It must be good. And actually there was a professor here at NPS in the 70s that started testing it. And he found that it had really terrible characteristics. It was much less random than you would think. And so we kind of blew that out of the water. So the lesson is you just kind of know what you're using in this. Okay. So, and that's, so what that means is that going forward, we can assume that there is a source of these independent, identically distributed uniform random numbers. And depending on how much risk you're willing to take, if you're on a computing platform, there is one, whether you want to use the good one or not. So that's always available. So now, if that's all that you could do, then it wouldn't be terribly useful, because as you've noticed, hopefully, we've wanted to, for every probability distribution that we might want to use in our model, we want to be able to generate from that, because if we can't, then what's the point? So that's what random variate generation is all about. So what random variate generation is assuming we have a sequence of pseudo-random numbers, meaning, they're uniform 0, 1. And what we want is another sequence. We want a sequence of independent, identically distributed random variables, but with a different probability distribution. So like when we said we want an exponential, well, we have a bunch of uniforms, but I want an exponential. We have uniforms, but I want a gamma, I want a beta, I want a Pearson type 6 distribution, whatever that is. And so the idea is that we want to apply a transformation to those to produce this value. That is, how can we transform these uniform 0, 1 random variables into one that has a distribution that we want? And now this was kind of back when I was sitting where you are. I mean, not literally, but when I was taking my class in this, this was the big focus. This how do you do that? This was back when dinosaurs ruled the world, of course, and so there was a lot of effort in coming up with ways of doing this, and it was very active for a long time, and then they basically kind of pretty much plowed that field out. So what we're gonna cover are just 3 general methods, and there are a bunch of special ones which I'm not going to cover. Again, like we spent the majority of back then it was semesters rather than quarters for the place I was, and we spent the majority of it in studying different ways of generating these random variable distributions. Why? Because that was still something that was being developed. So what you're going to come away with are just sort of 3 general methods. And my experience has been that these 3 general methods will provide the ability to create whatever distribution that's on the table. And so you might be thinking, well, SimKit has a rather extensive list of these random variables. The Python one has a slightly smaller list of these. And so you might be wondering, okay, why learn all this stuff? We just kind of use what's there. I guess I feel that I would be doing you a disservice if I didn't give you methods of coming up with it. Several reasons why. One is that you may be in a situation where you're on a computing platform that is not of your choice, and you have to generate these things. And so if it isn't provided by the computer language that you have, but you need them, you need a way of producing them. And so after this module, you'll have a way of producing pretty much any of the standard distributions. The other is that even if there's, and this is something I discovered when writing SimKit, it was like, okay, ideally, I would have every single probability distribution that was out there as one that you could just call on and do. Realistically, that's not possible, because there are actually a ton of these. There are all kinds of weird distributions, and in fact, I'm gonna make you apply some of this stuff to some of these weird things where you'll have to kind of Google what they are. So even if you have a list, there's always going to be something that's not on the list. And so why is that an issue? That's an issue because where do these come from? Where do these distributions come from? Here you're being handed them. You say, okay, use a gamma for this, use a Weibull for that, because I'm handing them to you. Where do they come from? Well, ideally, you're collecting data from the thing you're trying to model, and then using statistical methods of fitting a distribution to it. And there are, it may be that the distribution that best fits the data is one that's not on the list. And if that's the case, then, imagine briefing the results of your analysis, and you have to say, with all honesty, well, the data showed that this was a Pearson type 2 distribution, but the software we had couldn't generate a Pearson type 2, so we just used an exponential. Well, that's not going to be a very pleasant brief. If you're saying, okay, it should be this, but we actually use that, so why should I believe anything in your results if you're not using the distribution that actually fit the data? And if that distribution is not one on the list, then you need a way of doing that. So now you have no excuse. Well, not now, after the next segment. So tomorrow we're gonna start with this inverse transform method, and it's going to we're gonna use a bunch of math. You've all had calculus. It's not going to be a lot of calculus, but it's going to be a little bit of functional stuff. So, for example, and for some reason, the math classes don't emphasize things like if you have a function, how do I take the inverse of that function? You all know what an inverse function is, right? But how many times have you actually taken a function and computed its inverse? Never. I mean, unless they've changed the curriculum since I've been through, which they probably have. It's been light years or parsecs or whatever. But the fact is that if I have a function and I want to compute the inverse, then basically, if you remember, what is a function? A function is here, like I give you an x value, and then this gives you an f of x value. So how does the inverse work? The inverse is I give you the function value. So let's say I give you this value, and then I want to figure out what the inverse of that is. That's what's down here. And for some reason, it turns out that activity is what is behind the inverse transform method. We'll go into that in more detail tomorrow. But for some reason, it's not really taught, so I'll have to talk about it. Anyway, okay, so we're about to, the next step is we are going to take these, we're going to assume we have uniforms, and we're going to assume that they're good, and so we want to take them and turn them into a distribution that we want, and that will be next time. And if there's nothing else, okay, so now who was it who wanted me to hang on for a little bit?
That'd be me, sir.
Okay. Okay, go ahead.
Sure thing. Do you mind if I share? Oh, looks like it's okay. There we go. We want